Welcome to The Explainer. Today, we are going to crack the code on a programming concept that's, well, it's incredibly elegant, but let's be honest, it can be a little mind-bending at first. I'm talking about recursion. So let's demystify it together.
So let's kick things off with a bit of a puzzle. What could possibly be the hidden link between a sprawling family tree, the infinite repeating patterns of a fractal, and, the very folders you use to organize your computer files? Well, the answer is a pattern of self-reference. And that one idea, that's the key to everything we're about to explore.
Okay, let's dive right into this. At its heart, recursion is about tackling a huge problem, not by trying to wrestle with the whole thing at once, but by breaking it down. And here's the magic trick. You break it into smaller, identical versions of the exact same problem. You keep doing that until it becomes so simple you can solve it without even thinking.
Now, to get this really powerful idea working in our code, every single recursive function, and I mean every single one, relies on two critical parts. If you can understand these two pillars, you've pretty much built the foundation for mastering this whole thing.
And here they are, the base case and the recursive case. Just think of the base case as the stop sign. It's the simplest possible version of the problem that says, whoa, stop, I know the answer to this one. The recursive case, on the other hand, is the engine. It's constantly saying, this is still too big. I'm going to call a smaller clone of myself to handle a piece of it. These two have to work in perfect harmony for any of this to work.
Okay, theory is one thing, but it's another thing to see it in action, right? Let's make this real with a classic example every programmer learns, calculating a factorial. We're going to see exactly how a recursive function figures out 3 factorial, which is just 3 times 2 times 1.
The key thing to understand here is that the logic is beautifully simple. The recursive case says that the factorial of any number n is just n times the factorial of n minus 1. It's basically just passing the buck to a slightly smaller problem. So where does it all end? Well, that's the base case. The second n hits 0, the function just says, okay, the answer is 1, and that ends the whole chain reaction.
Okay, so you might be wondering, how does the computer not get totally lost? How does it juggle all these nested calls to the exact same function? Well, to get that, we need to peek under the hood at the brilliant little machine that makes it all possible.
The secret weapon is something called the call stack. I want you to imagine a stack of plates in a cafeteria. Every time a function is called, a brand new plate is placed right on top. And this plate, which we call a stack frame, holds all the info for that one specific call. The computer, it only ever pays attention to the plate at the very top of the stack. Let's actually trace this with our factorial of 3 example. First, the call to factorial of 3 gets placed on the stack. But it can't finish its job until it knows the answer to factorial of 2. So a new frame for that call gets stacked right on top. And this just keeps going. A frame for factorial of 1 goes on top of that. And finally, a frame for a factorial of 0 sits at the very peak.
Now, this is where the magic really happens. We get to watch the stack unwind. Factorial of 0 hits our base case and returns the number 1. Its work is done, so its plate is taken off the stack. That return value gets handed down to factorial of 1, which can now finally finish its calculation, and boom, its plate is removed. This cascade continues all the way down until the original factorial of 3 call gets its answer, and the stack is finally empty again. Pretty cool, right?
So, we know how it works, but the bigger question is, why would you even bother? When should we reach for this tool? Well, it turns out this recursive way of thinking is like a superpower for solving certain kinds of problems with just astonishing elegance.
Its first superpower is what we call divide and conquer. This strategy is absolutely perfect for any problem you can split into smaller, independent chunks, solve each chunk separately, and then just stitch the results back together. This is the core idea behind some of the fastest sorting algorithms out there, and it's the most natural way to explore data structures like binary trees.
Its second power is backtracking. Think about solving a maze. You go down one path, and if you hit a dead end, what do? You backtrack to the last intersection and you try a different route. Recursion manages this whole process of exploring every single possible path automatically, which makes it an absolute beast for solving puzzles like Sudoku or navigating complex decision trees.
And finally, some data structures are just built for recursion. I mean, think about a file system. A folder has files inside and, well, more folders. Each of those subfolders is its own smaller version of the exact same structure. So if you write a function to find a file, it'll check the current folder, and for every subfolder it finds, it just calls itself.
That right there is recursion in its purest form, and it's the exact logic behind something like a depth-first search. But, this superpower does come with a bit of a dark side. It's an incredibly powerful tool, but if you're not careful, it can lead to some spectacular failures. So let's cover the essential rules of the road to keep your code safe and sound.
The most infamous pitfall, one that a whole website is even named after, is the stack overflow. This is the crash that happens when your function just never stops calling itself. It keeps piling those plates onto the call stack, higher and higher and higher, until the computer literally runs out of memory. And this is almost always the symptom of a broken or a missing base case.
So to stay out of trouble, you just need to follow 3 simple rules. 1. Your function must have a base case. No exceptions. 2. Every recursive call you make has to be taking a step closer to that base case. And 3, for problems that might need thousands of recursive calls, just remember the call stack isn't infinite. Sometimes a simple loop is the safer, more memory-efficient choice.
So you've seen the theory, you've seen the mechanics and the dangers. How do you really get a feel for this stuff? How do you make it second nature? Well, like any skill, it's all about starting small and building up your confidence through practice.
We've laid out a little roadmap for you here. Start with the basics, things like factorial or summing an array, to really nail down that base case, recursive case rhythm. From there, you can level up to intermediate divide and conquer challenges. Once you're comfortable with that, you'll be ready to take on the truly advanced backtracking puzzles that show what recursion is really capable of.
So let's bring it all home. At the end of the day, recursion is a way of thinking where you solve a problem by defining it in terms of itself. It's this beautiful dance between a recursive case that breaks things down and a base case that stops the music. The call stack manages all the choreography behind the scenes, making it a perfect tool for these self-similar problems, as long as you watch out for that stack overflow.
Look, in the end, recursion is more than just code. It's a whole new lens for looking at problems. It's about spotting those hidden repeating patterns that are all around us. You have that lens now, so the only question left is, what complex problem are you going to solve with it first?